Well, hi again. This is Bob, and I'm over on page, the bottom of page 426. Oops, it's 8.2, part 1 that we're talking about. And I know in section 8.1, I talked about how much theory there was, and we had a lot of definitions, and we had a lot of the book leading us to the use of z-values with the idea of a critical value, and then the critical and non-critical region, and null hypotheses and alternative hypotheses. Fortunately, we didn't really have anything to build on in 8.1. But now we do. In 8.2, we're going to work carefully through three examples, and the examples are for right tail, left tail, and two tails. And as we work through those three examples, we're going to see exactly what they were trying to get at with the theory in 8.1. So just to review a little bit, we have the null hypotheses and alternative hypotheses. We drew a diagram, standard normal distribution, if you will, and we showed for how if we had a excuse me, two-tailed test, we would have a critical region, a non-critical region, excuse me, and then in the tails, we would have critical region, which I'll just, for time's sake, abbreviate CR. And each of those critical regions would be set off with a two-tailed test with a z-value, a positive and negative z-value, in fact, for a two-tailed test. Okay, and then I mentioned if we had, for example, a right-tailed test, then this would be the non-critical region, and at a certain alpha or confidence interval or percent, this would be the critical region, and this would be set off by a positive z-value. Now, I'm not speaking yet directly to what we're going to do, but I did hint on that. Then the last situation we're going to run into, or the last of the situations that there can be, would be if we had at a certain alpha where we had a left-tailed test. This is in the situation where we believe our sample mean is significantly less than the population mean, and in that case we would be evaluating with a negative z-value as our critical value. And just to remember, because we saw some other things, we saw where we had the null hypotheses for, let's say, for two-tailed test, just we'll get it all in just a second here, would be that U equals a parameter, and our alternative hypotheses would be it doesn't equal the parameter. And of course, what we're talking about in this section is a sample mean. Okay, and finally, on the top of page 427, we see our old standby from, we began it on chapter 6 and refined it on chapter 7. Remember also we had the central limit theorem. Now, we first started off figuring out a z-value for one person pulled out of a population, and then we learned about the mean of the sample means and the central limit theorem and a correction on the mean. You may recall that that was chapter 7 stuff, and how we can pull out a large sample and find out that sample mean, but we found out that we had a change in the denominator. We divided the population standard deviation by the root of our sample. You may or may not have to go back and review some of the things with the central limit theorem, but if you remember how it works and how to use it, then I think you'll be fine. And finally, I'm trying to stay away from so much theory in this lesson here. they tell us, and of course I'm expecting that you've already done or will be doing shortly after I hit the high points here, a close read. But before we finally get into using this, they give us a couple of assumptions for using the z-test when we know the standard deviation, by the way. And the sample is either a random sample or the number in the sample is greater than or equal to 30, or they tell us it's normally distributed when n is less than 30. And that's about halfway down on page 427. Then they give us below that, and it's important that I at least mention this, they give us 5 steps when we're going to test a hypothesis. And the first one is to state the hypotheses and identify the claim. To me, the claim isn't as important, but I will mention it in passing, and I'll refine that a little bit later. Then we're supposed to find the critical values. Those would be z-values. But again, I remind you that they've given us all the z-values that we need for these questions over on page 422. So we don't have to go back to the tables and find a z-value for a certain confidence interval. They're all summarized in the previous page on page 422, just a few pages back. Okay, once we find the critical values, then we'll take the information and compute the test value using this formula right here. And then once we have the test value, we'll compare that test value with our critical value, and that will help us make a decision as whether or not to reject the null hypothesis. Recall, the null hypothesis says there's no difference between a parameter, that's like the actual population mean, and a specific value like a sample mean. And then we summarize our results. Now they tell us that there's a lot of terms and a lot of things going on, but I promise you after working these 3 examples that we'll get the mechanics of the formula. And I'm going to start off, just for the sake of space here, on example 8.3 by listing all the information I can, then going to the question. That always seems to work out best for me. Of course, you not only have the examples, but you'll see in our student solution manual where they list all the information and they actually work the problem out and give the interpretation also. But they tell us that a researcher in 8.3 at the bottom of 427 believes the mean age of medical doctors in a large hospital system is older than the average age of doctors in the U.S., which is 46. Well, as soon as I can come up with any piece of information, I'll write it down. And then this researcher believes that the age is actually larger, older, and we have given a standard deviation, population standard deviation of 4.2 years. I'm just writing information down as it comes. And the researcher did a random sample of 30 doctors. Okay, and from the random sample of 30 doctors, they found out that the average age was 48.6. That's a sample mean. I'll put years on here just so we don't mix up our units here. Okay, and then the last thing that they want us to do is test the claim. Now, what they're saying for the claim here, and sometimes the claim is hard to, I shouldn't use the word hard, but it can be challenging to identify it because they just don't use the word claim. In every, if I do give you a test or quiz question, and which I don't recall giving any, but I will actually use the word claim. Like the way they word it here is the researcher believes the mean age of medical doctors. They could have just said a researcher claims, but they didn't do that. They used believes. But in this case, the claim and believe, and I guess if we did enough of these with and usage of English language, we would be able to pick out the claim quicker. But the claim is nowhere near as important as our decision to reject or not reject the null hypotheses. It turns out it's just another way to express our answer. So I'm not going to downplay its importance, but I'm just going to say that I'm more interested in yes or no as to the null hypotheses being rejected. And that's the way I word all my questions. Anyway, excuse me, I've got a lingering frog in my throat here. Let's look on the top of page 428 and go through the 5 steps. And the first one is to identify the hypotheses and the claim. Our null hypotheses would be that the mean is 46 years of age, and the alternative hypotheses, which the researcher believes is correct. In other words, the researcher is challenging the established age of doctors. He's saying he believes, or she believes, that it's larger. And it just so happens in this case that this is the claim. But the claim can also go with the null hypotheses. But again, it's the book's way of approaching this, but I prefer the way where we just say we reject or we don't reject, and that'll make more sense in a few minutes here. Anyway, the next thing we would need to do is recall that we have an alpha of 0.05, I believe. Shoot. And that's the same as like we're talking about, we're 95% confident of our answer if we want to go back and look at this in interval terms. But here's what that really means. It means that 95% of the graph would be non-critical, and then we'd have 5% in the right tail. Remember, when we are using a larger or greater sign in our alternate hypotheses, it's immediately understood to be a right-tailed test. Okay, so what we would need to do in the book would go find the closest value in the z-tables to 0.95, and it would be everything to the left of this critical value. But we don't have to do that. This is a right-tailed test at alpha 0.05. If we go back to page 422, they tell us what our critical value is. They tell us it's 1.65. Now, you know how to find it by going back to the tables, but we don't need to do that. We're going to concentrate on the flow of the problem here. Okay. I think the next thing we'll do is from the steps, this would be step 3, is to compute the test value using our formula here. Now, I'm going to not actually pull my calculator out and do this, but I've reviewed the question ahead of time, and it is correct, their work. But make sure that you physically do this so you know how to input things in your calculator. Now, when we do the question, we end up with a z-value of 3.39. Okay, so this now will help us determine whether we're going to reject or not reject the null hypotheses. Our cutoff value, this was the 0.95 that was non-critical, and this was our critical region. It's just a little drawing to help me, and I recommend that you draw one also. Okay, our critical value that our z-value that we calculated was 3.39. Well, that is well beyond the 1.65 that our critical value. I'm sure you'll agree that 3.39 is greater than 1.65. We're much further into that right tail with 3.39. Okay, now we can interpret our answer statistically. When I say that, I mean using our standard normal distribution, we have come up with an answer, 3.39, that is way beyond the critical value of 1.65. So we look back at this null hypothesis that said the mean was equal to, what was it, 46. And statistically, and when I say that, I mean by using our tables, we've come out with a mean, with a z-value that's much larger or further into the tail. And since that's the case, we reject the null hypotheses. Now, if we got an answer when we calculated, let me just go back a page here. Try to go back a page. Let's say that we got a z-value that was like 1.4. Okay, and then if we go back to our drawing, clearly 1.4 would be somewhere in the non-critical region. Okay, so if we had got 1.4, which we know is in the non-critical region, then we would not reject the null hypotheses. Okay, we would say that the alternative hypothesis is not true. Anyway, we've rejected the null hypotheses. That's what they say in step 4, since it's greater, 3.39 is bigger than 1.65. And then for step 5, they summarize it. I would summarize the results just by saying there's enough evidence to reject the null hypotheses. The book summarizes, and it's saying the exact same thing, is that there's enough evidence to support the claim. Well, remember that the claim, in the case of the claim, it went with the alternative hypotheses. So the books, and both ways are fine. In fact, I prefer just reject or don't reject null hypotheses. But the fact that the book chose to word this as there's enough evidence to support the claim, that means the exact same thing as the evidence was there to reject the null hypotheses. It's just a different way of phrasing the answer. And as I mentioned, I prefer reject or not reject, because I don't particularly, I haven't entirely bought into the idea of claim. Some books do, and others don't stress it as much, but we'll cover it and make mention of it also. By the way, there's a little blurb right directly below step 5 on page 428. They say, in this example, we have is statistically significant, but don't forget that we're at the alpha equal 0.05 here, and that alpha is our area of doubt, and we can't be 100% sure that we have correctly rejected the null hypotheses. We can be 95% sure because that was the area in the non-critical region, but the book reminds us that we are subject to a type 1 error. That's when you reject the null hypotheses and it's really true, and we have a 5% chance of making an error in this question. That's what they're trying to say in that comment. Okay, well, let's take a look at the second example. It's example 8.4. And it looks like we've got 36 math SAT squares there, SAT scores, and they tell us that the variable is normally distributed, which we need to know, and they tell us the population mean of 515. They tell us that the standard deviation on the math portion is 100, and we've got a superintendent who wishes to see if her students, I guess it's a superintendent, reading them, it is not that it matters, but yes, it's a superintendent, wishes to see if her students scored significantly below the national average. Well, when the tip-off with the word below, is that sets us up for a left-tailed test. There would be our critical value, etc. So let's see what we have here. I'm going to take the book's word on some of this. Fortunately, we don't have to go back to chapter 3 and work through that long calculation of finding the sample mean. They've done it for us. But we know just from a brief read that the population mean score on the test, if you will, is 515. We are given the standard deviation of 100. We know the size of the sample that we're using is 36, and we know that we're alpha 0.10. So now that I've got that information, I can concentrate on setting up a situation, and of course I always recommend that you draw a raw bell curve and list the important items. It's not much, okay? We're going to have a critical region here, and that will be 0.10. That's our alpha, if you will. And then the other 90% is the non-critical region. Okay, and of course this is our critical region. Okay, so we're going to have to come up with a z-value here, and we could do it directly by going back into our z-tables, our negative z-tables, and find the area represented. But there's a much simpler way to do it, and that's to go to page 422 and just look it up. Alpha at 90%, or alpha equals 0.10, or 90% confidence, and we would find out that it's minus 1.28. Okay, remember we have 3 confidence intervals that we almost always use: the 90th, or 90%, 95%, and 99%. And for left tail, right tail, and two tails, they're all represented on, all the values are given on page 422. Well, so here's where we're at now. We haven't given the hypotheses yet, but we've sketched the situation, and we know what our critical value is, and we know where our critical areas are, critical, non-critical. So let's go ahead and write our null hypotheses. The superintendent, if you recall, wanted to see if her students scored significantly below the national average, kicking us over to the left side of the graph. She wanted to check if they were above the national average, then would be on the right side of the graph, or right tail, I should say. Anyway, the null hypotheses would be that the mean is 515, unchanged between the mean and any other value, and the alternative hypotheses would be that her students scored less than 515. And that's what she's checking, and it just so happens that in this case that would be the claim. Now, they could have worded the problem that the superintendent claims that her student score were less than 515, but they didn't use the word claim. They said she wanted to see, okay? So that just gets interpreted as claim. Anyway, we now have enough information to go ahead and compute. Recall that the sample mean, if I didn't write it down, it turned out to be 509.028. Well, that is less than 515, but we don't know yet if it's statistically or significantly less. Okay, so we just can't reject the null hypotheses until we put the values on it. And I'm going to leave the calculations of this one to you. You can follow them, and I'll just want to concentrate on the interpretation here, because we've done quite a number of these z-value calculations. They get a z of negative 0.036. And let's go back and sketch this. This would be our mean here, if you will. And here is our cutoff value, and that was minus 1.28. When I say cutoff value, minus 1.28, I mean our critical value. And of course, all this would be non-critical. Well, notice that negative 0.36 is to the left of our 0 there, our mean. However, it's just a little to the left. It's certainly not less than negative 1.28. So we're on the left side, but we're nowhere near mathematically. In other words, we do not have a calculated z-value that's less than minus 1.28. Now, if we would have got like minus 1.52, that would have been further over in the tail, we would have rejected. But we only got negative 0.36, which is just a little bit away from our mean there. So we do not reject the null hypotheses. I'm just going to say that right now. Don't reject okay? And they discussed this. I'll just go ahead and read the rest of it. You can follow. Now, their diagram's a little nicer than mine, but it's the same idea. They say, since negative 0.36 falls in the non-critical region, the decision is not to reject the null hypotheses. And then to summarize the results, I've already summarized, don't reject the null hypotheses. That's my conclusion. There's not enough evidence to reject the null hypotheses. They summarize by saying there's not enough evidence to support the claim that the student scored below the national average. Okay, they did score slightly below, but not enough to reject the fact that the national average was 515, or where they fell in with regard to that 515. So I'm going to read their little comment because this is good for interpretation. Even though their sample mean 509.028 is lower than the hypothesized population mean of 515, it's not significantly lower. The difference may have been done, maybe due just to chance. Okay, so that's our interpretation of that question there. Well, let's go look at their last example. And this one is kind of wordy, but it's on the cost of rehab for hospitals and averages, and it's on page 430. Now, remember we have 3 tests, left tail, right tail, or 2 tails, and this is a 2-tail test, and whenever we have a 2-tail test, we expect we're still going to have a null hypothesis. Lost my pen there. And that null hypothesis is going to equal, just for the sake of a number, I'll say the null hypothesis of some situation is 40. Okay? Well, if we do not know ahead of time whether we expect our alternate hypotheses to be bigger than 40 or less than 40, when we don't know, in other words, if it's a right or a left-tailed test, then our alternative hypotheses, we use the not equal to sign, because we don't know where whether the region, or I should say whether the mean is going to be, or our z-value will be, we don't know which side of the normal distribution that our z-value is going to fall in. Okay, so that's when in the past we've had the situation for a 2-tailed test where we've had a positive z-value and a negative z-value. Okay, and of course these would be our critical regions and this would be our non-critical region. Now they've shown all that on the middle of page 430 there. But let's go ahead and see if we can follow along with this question and find out why it's 2-tailed. And I'll read through the important part first. The average cost of rehab for a stroke victim is $24,672. I might as well write that down right now. And the researcher, trying to get everything correct in this question here. Who is this person that's in a different particular hospital? Yeah, a researcher did a sample of 35 stroke victims. Again, it's just helpful for me to get as much information as I can at the very beginning, and found out from that 35 stroke victims that the average cost was $26,343. That's our sample mean. Okay, and the standard deviation of the population was 3251. I'll put some signs on these here just so we know we're talking about money. Okay, and then the last thing that we need is we're supposed to set up a confidence interval of alpha 0.01. Okay, well, I can use that in the next page, but let's go see why this is a two-tailed test. We have the average cost of rehab at $24,672. To see if the average cost of rehab is different at a particular hospital, a researcher selects a random sample of 35 stroke victims. Notice the researcher they don't say the researcher believes the cost is more than $24,672 or less than $24,672. The researcher is basically questioning whether, in other words, it's not a right or a left-tailed test. They're questioning the average cost, but they don't know whether it's going to be more or less. Okay, so in other words, our z-value could fall on, our calculated z-value could fall on either side of our symmetry line. So let's get our hypotheses up there. $24,672 for our null hypotheses. Now, when we don't know, as the researcher doesn't know whether this average is going to be more or less, we use a not equal to sign. That's what makes it two tails, because the value, our critical value, could go either direction. And they tell us that that is 24672 is our claim. In most cases, when we question an established mean, that's the one that the claim goes with. If I had worded that question, I would have started off by saying a researcher claims that the average cost for rehab of stroke victims is not $24,672. I would have worded that question differently. Anyway, let's go draw our situation now. It's a two-tailed test, so the answer could fall in either of the critical regions, and that always happens in the tail as the values, the z-values tail off. This would be, we were at 0.01, so 99% of the graph would be here. And recall, if alpha equals 0.01, when we divide 0.01 by 2, we get 0.005. Okay, and of course we can go in the back of the book and find the closest z-value that would represent the area to the left of, on this, we could use the positive z-values to get it directly. But why don't we just go back to page 422 where they give us, for a two-tailed test, the z-values at alpha being 0.1%. And it turns out that they're negative 2.58 and positive 2.58. So now we have everything ready to plug into our formula. And concentrating again, I expect you to work through that and double check. When they use that formula with the values, they end up with a calculated z-value of 3.04. And going back to the situation I just drew, I'm sure you would agree, let's say that 3.04 is right here. Well, that's much further, well, much is a relative word, but it's certainly further or deeper into the tail than, in terms of area, than 2.58 is. Said differently, our z-value of 3.04 is greater than 2.58. And since that is the case, we will reject the null hypotheses. Okay, and that would be our step 4, reject the null hypothesis since the test value falls within or in the critical region. Now, they summarize again using the term claim. They say there is enough evidence to support the claim. Oh, excuse me, I guess in this case, let's see if they didn't make a typo here. There is enough evidence to support the claim that the average cost of rehab is different. Okay, yeah, it was, our null hypothesis was that the price was 24672, and our claim said that it wasn't. So in this case, and again, this is why I prefer just one way to say this, but in this case, the claim went with the alternative hypotheses, and it turns out in this case, the alternative hypothesis was true, and that was that the mean was not equal to 24672. Personally, I say reject the null hypotheses and move on, but since they introduced the idea of a claim, we're going to say there, as the book did, that there's enough evidence to support the claim, okay, that the average cost is not $24,672. Okay, well, I broke this 8.2 into 2 parts because the second part basically does the same thing that we've been doing here, but it deals with the actual area when we're talking about the actual area in a tail. In other words, when we set off like 5% as our area in the tail that's associated with a z-value, we're going to solve I'm just giving you a little heads up on what's going to happen in the next lesson. If we get a z-value, let's say in this situation here, that's greater than the z-value at the critical value, instead of just immediately saying reject, we're going to give the actual area. In other words, we'll get our calculated z-value, and if it's larger than our critical value, we will give the area in this case, in that right tail. It may sound a little wordy now, but like everything else, once we do a couple of them, and you may want to look on the top of 431, and this might be one of those sections that is really extra helpful to read ahead so you have something to build on. Anyway, I will be back shortly with the second part of 8.2, and you may, in the meantime, want to just go ahead and work a few of the homework questions that dealt with the procedure that we just did, not the p-value. All right, I'll be back shortly. Thank you.